Hello and welcome. This is Dr. K, and today we're going to talk to you about why you should probably be using maximum material condition on your position tolerances. Alright, so today we already talked about position and how we're going to deal with our features of size and work through and run a position tolerance, and depending on the feature, whether it's the whole feature or some sort of slot feature, we may be dealing with parallel plane position tolerances or circular position tolerances. So why would it matter if we were to apply those tolerance zones at our specific material condition boundaries? And of course, the two that we have to work with are maximum material condition and least material condition modifiers. And so what does it mean? Why do we do that? Well, something to consider is that if we have parts that are going to be assembled together and we want to ensure that there is a certain hole that's left, so in this part here we want to ensure that no matter where this hole gets produced, that as we assemble it, the hole that's left over there is always going to be there. So as this hole shifts around, there's a hole that's the size of this pin in this particular example that's always there. We might find ourselves in a place to use the maximum material condition modifier for the holes. The same thing applies to the pins here. Now these are pins. They could also represent like a bolt that's going through this. It'd be a little bit different, but I'm trying to keep the example here simple. But if we dealt with the position of this at maximum material condition, again, there's going to be a certain size or a certain envelope that this pin theoretically could be in. And as long as it matches up with where the hole is, we're always going to find ourselves in a place where these two pieces will mate together. Now that pretend size that this pin theoretically could occupy is what we call the virtual condition. And what I have here is I'm going to give a little example on the piece of paper what virtual condition looks like for a pin and for a hole. So let's talk about one of these pins. One of these pins, we're going to assign some sort of position, a position tolerance, and that position tolerance is going to be a cylinder of a certain diameter. And so I'm just going to use this and draw as best I can. May not be that good. Oh, it's horrible. But we're going to draw a circle that represents that diameter, whatever that tolerance happens to be. So let's say it's 1/4 inch. And so we have two conditions that really come by for this particular hole, or this particular shaft in this particular case, is we have its maximum material condition and its least material condition. What we want to look at is what envelope does that particular part encompass at those two conditions. So what I have here is I have a little target, and we're going to pretend like this is what the least material condition, right? This is the smallest shaft. And so something to consider is that as the designer, and the shaft is the smallest shaft, and we look at how this thing can vary in position, well, let's look at the extremes here. This part could shift all the way to the left. I'm going to draw a little guy over here. It could shift all the way to the right. It could shift all the way up. And it could shift all the way down. And of course, if we really got excited, it could shift all the way to that corner, to that corner. And of course, if I was to draw these all out, we'd get all kinds of circles. But essentially what we have here is we have a circle, an envelope that at least material condition, this part is able to occupy. And so essentially for this particular part, we say, all right, it can vary by this amount. So for at this particular size case, this is everywhere that it'll envelope. Okay? Makes sense? We got that. That's least material condition. But here's the part at maximum material condition. So it's a lot larger part. So you'll see here that we have this strange thing. So essentially, if the pin is created as this largest pin, and we come over here, well, now we're dealing with a size that, of course, is a little bigger. Right? We come down. We do all these variations. I get these extra last ones just so that my circles don't look too crazy. And here we are here. So I'm going to use a marker. So at maximum material condition, we're allowing this shaft to occupy this space. So the question that will come up is, let's go back to the least material condition case. If at maximum material condition, we're going to allow the pin to occupy this area, why can't at least material condition the pin occupy that same area? So essentially, why can't the pin be produced over here if we're going to allow that same pin to occupy this area here? Can we think of a reason why this pin position wouldn't work if we're going to allow this pin? You know, if the pin itself is going to occupy this space at the largest condition, why can't it at the smallest condition occupy that same space? Any ideas? Well, I don't know either. I can't necessarily answer that question for you, but for the most part, in almost all situations, you're going to say, you're absolutely right, Dr. K. There is no reason why at the least material condition, this particular pin can't occupy that space. And so that is the reason why we have the material condition modifiers. So what's that do for us? If we take our tolerance, we have a position. Remember how this works? We have a diameter. We have a size. Oops, in this example, I'm putting 25, whatever that example is. If we state that we're at maximum material condition, that we're going to apply this tolerance at maximum material condition, well, what is that for our pin? That is this guy here. So we're going to apply this tolerance at maximum material condition. So that gives us this outer boundary. That is what we call our virtual condition for this part. It is the theoretical maximum boundary that this part is going to fit in. What this modifier does for our tolerance is gives us what we call a bonus tolerance. And that bonus tolerance is equal to the deviation that we are from maximum material condition. So as our shaft gets smaller, every thousandth of an inch that our shaft gets smaller, this circle grows by a thousandth of an inch. So you can imagine what that does is as we move closer and closer to the least material condition size feature, our bonus added to this position will yield us a part that is allowed to come all the way out here. So technically, given these crazy graphics that I have going on here, our position tolerance would increase. Again, what we're doing is we're allowing for when we are at the smallest part, in this particular case at our least material condition, the position can shift all the way out. And this allows then for this position, for this feature at the least material condition to fit still inside that virtual condition, and the part's okay. All right, so now let's reset, do the same thing. This time though, we're going to talk about this hole. So here's our position, here's our tolerance. We have a position tolerance. We'll just use the same examples we had before. It's a diameter, 0.25. We've got 3 datums somewhere, or at least a datum reference frame. So here's our position. So again, now we're going to talk about the hole. So our least material condition, that's the hole that's the largest. So again, this one's a little bit different in that now we're talking about the hole that's passing through. So my example here, I'm actually going to run the back side of this. So it's a little bit stranger. But at our least material condition, the hole that's left over, if our part is able to be produced at all these different places, looks something like this. Right, so there it is there. Let's fill it out. So at our least material condition, here's the boundary that we're allowing. Okay, got that? All right, so let's go to our maximum material condition. So at our maximum material condition, we get this strange guy that's coming along. Again, we're talking about the hole, so it's just the opposite of the, let's see, away, 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 and away. So at maximum material condition, this is the hole that's left over. So again, just like the last one, this is our virtual condition. We are saying at this size hole is always going to be left over. If we build thousands of these parts and we line them up by the datum reference frame, theoretically we will see a hole that's that size going through the whole thing. We'll always be able to put a pin that's that size going through the whole thing. So again, the same thing happens here, is that if this is the hole we're going to allow, let's go back to our least material condition case here, which really means this hole going all the way over here. If I was gonna line up this condition, line it up here, we're talking about a position that's way out there. Same thing over here. Now it just happens all these are really close to the same size. Just know that that's just incidental a little bit in the example. But essentially for me to be able to, at least material condition, have this same virtual condition, we have to allow the tolerance to increase as we move away from the maximum material condition. And so it applies the same here. When we add maximum material condition to the part, we are saying at the maximum material condition, it can only be 1/4 inch. But as we get larger, as the hole gets larger, every thousandth of an inch the hole gets larger, we can deviate from this 1/4 inch by 1,000th of an inch, all the way up to the maximum material condition where we're able to deviate the most amount. And so this allows us to maintain this same virtual condition. So even if the holes are made at this size, we're still allowing this size of hole to come through. Now, what I'd like you to do is think about what this means in the least material condition case. It's just the opposite. We're going to apply the tolerance here at least material condition. And then as we get away from the least material condition, go to maximum, we're going to start adding that tolerance. So for a hole, it's going to seem a little strange for either a hole or a pin. It does have its applications. I'd like you to think about that and where you might apply least material condition when it comes to features. So I started this by saying more than likely for your features of size, especially if they're holes or shafts, you will want to apply maximum material condition modifier. Why is that the case? Well, for most things that assemble, the maximum material condition where we gain this bonus tolerance and we maintain a certain size virtual condition allows us to assemble parts. This also then means that we're talking about aligning parts. We're ensuring that parts are aligned by a certain amount. A very helpful thing that happens when we use maximum material condition is that when we go to inspect a part like this, more than likely we can create a gauge to inspect the part. So ultimately here, I use this as my example of assembly, but for a part like this, the gauge that checks the part may look something like this. And you could imagine that if this was a gauge, that these pins were created as best as you can in position, so virtually at a perfect position, and were created at the size that is this virtual condition. All we have to do in this particular case to check to see if this part is okay is put it in my gauge. If it fits in the gauge, the part's good. Now for a part like this, we would also then have to make sure that the least material condition is met. So we'd have to measure each of these holes and make sure that they weren't too large. As long as they weren't too large or too small, we could check both their size, make sure they're not too large or too small. As long as they're not too large or too small, I can place it in the gauge. If it fits in the gauge, it's a good part. When you deal with parts that are, regardless of feature size, do not have this, well then we need to do some other method. The gauges get more complex if you can use a gauge, or we may be dealing with some sort of coordinate measuring machine to inspect these parts. And that's an important aspect to remember as we're designing and creating our parts is that in manufacturing, they do need to be inspected. All right, so this is not everything that has to do with maximum material condition. I am not going through the math of maximum material condition. There is kind of math that's involved. It is very easy math, but I'm not going to do that here. I just want to get you dialed into the concept and just start thinking about what maximum material condition means, or what a material condition modifier means to your feature, and at least think about why I should use it or why I shouldn't use it. What am I gaining? What am I losing? It's all going to come back to, essentially, and I don't know if I've talked about this before, but the function of your part. How does your part function? Can this help? How are we going to inspect the part? Can this help? Do we have these issues going on here in assembly? So there's a lot to think about. All right, so very simple overview of maximum material condition modifier, why I think you are probably under almost all circumstances going to want to use it for your features of size. So thanks for watching. I'll see you soon.